Hello. In this class, we will discuss random number generation. And as we saw in the last classes, this is one of the most important issues in Monte Carlo method. We learned that it's important to have a precise and uniform distribution of random numbers or uniformly distributed series of numbers in order to sample events according to a previous probability density. Okay, and this is the central issue in the Monte Carlo method. There are several ways to generate random numbers. The true random numbers are usually generated by some physical or natural method. You have to have some physical device. One instance is throwing in one die or dice. You can generate a series of random digits from 1 to 6 if you use just one die. If you use 2 or more dice, you can extend the number of digits. Roulette can give you large set of digits as well. And one way that we can generate random numbers is by using the chronometer. This was one problem left as exercise for you in the last class. So let's see here how you can use it.
So here I will show you how to use the smartphone or the chronometer in the smartphone to get random number series. I will start my chronometer here. It has this option to stop to mark the lap time. So I can just tap here and I get partial measurements of time, and I can repeat this process several times. And we get different values, and remember, we are interested in the last 2 digits of the time, and you observe that they are more or less randomly distributed. So this is a method to get random number series using your smartphone, okay? And you can repeat it as many times you need, but of course the precision is just 2 digits. It's not good enough for most of the applications of Monte Carlo we are interested in. Notice that you have at the end a series of numbers, and this series, if you get the last 2 digits, they are from between 0 and 99, and hopefully randomly distributed.
So the first Monte Carlo method was developed by Metropolis, who was a guy working with Fermi in the efforts to build the first nuclear pile in the United States. So nuclear fission was just discovered. There was the development of the nuclear bomb in the Manhattan Project. But Fermi notes that it could also be used to produce energy. And the nuclear pile was the prototype for the modern nuclear reactors. So the problem that they had was to calculate the probability of absorption of neutrons that are produced in the chain reaction in the nuclear pile by fissile nuclei in the parts of pile that contains the nuclear fuel. So a section of the pile is more or less like this. So this is pile is like a cylinder, and this is a section of the cylinder. You have water inside it, and these are the thin cylinders with the fuel, the nuclear fuel, which is composed of a fissile material, usually uranium. And what happens in uranium is that when it absorbs a neutron, it will undergo fission and emit, in the fission process, it will emit on average 2 neutrons. So these 2 neutrons will move inside the nuclear pile and can hit another uh, uranium atom and produce new fission. And so you have other 2 neutrons, and they have to control the number of neutrons that are captured by new atoms of uranium, or those that will escape, to control the critical value of the chain reaction, which must be about 1. It means that from the 2 neutrons that are emitted, 1 must be captured, the other one will escape from the pile. If you have less than 1 captured, the chain reaction will stop. And if you have more than 1, it's hypercritical and you don't have control, so it becomes a nuclear bomb. So it's important to have an accurate method to perform the calculations, and there is no analytical method to do that. So Monte Carlo method was the solution, and it was developed by this group, and Metropolis was the main guy working on this stuff. So, of course, as we saw, one problem was to generate a random number for the Monte Carlo method. And they didn't have electronic computers that were being developed just in that period, in another place by another group, as we see below. So they developed a physical method to develop, to generate random numbers. And this physical method was with a device called Fermiac, of course, based on the name of Fermi. And you can find a lot about it in the internet. So I suggest you to search in the internet for Fermiac and read a little bit about it. At the same time, von Neumann at another university was developing the first electronic computer, and it was called ENIAC. So ENIAC is a nickname for this electronic computer. And Fermiac, of course, was named after this ENIAC. So Fermiac was the Fermi method to develop, to generate random numbers and do Monte Carlo almost by hand, while von Neumann, his group, was developing a Monte Carlo, was developing an electronic computer, and of course, running the Monte Carlo there was one of the main objectives of this group. So there was, of course, a competition among them, and it's interesting, but this is a kind of sense of humor of academics. So Fermiac is named after ENIAC. You can find also a lot about ENIAC and the development of the electronic computer by this group. It's interesting to see that the first computers was huge and they occupy a large room in the building of the university. And its computational capacity was much smaller than what we have in a smartphone today. So it's interesting to read about it. So if you are going to generate random numbers in a computer, you have to develop methods for generating random numbers. And this is a sort of paradox, because a computer will follow a strict number of rules and will do every time all the same stuff. So how can you get random numbers in this process? And the first method was developed by von Neumann. And it's more or less what we have done with our smartphone or with our chronometer. I will show you in these 4 steps. You first select an initial number with a number A of digits, and it's called seed. and it's the same even today in the modern random number generators. You have to define a seed, and it will produce a series of random numbers. So you have to select an initial number, the seed, with 8 digits, and calculate a square, which will give you a digit with 2 8 digits. Okay, if you multiply a by a, you have 2 8 digits. And register the a central digits. So you have, as a result, a number with 2 8 digits. You select the a central digits, and this is your random number. Okay, then you can use it, this central digit that you get, the number formed by the central digits is the new seed, and you go back to step 1, and then you generate another one. So this process can be written as a software, and of course it's very fast, and you can generate, you can define random numbers with a number of digits a that's much larger than what we did with the chronometer. So you have high precision Monte Carlo with a fast method for generating random numbers. Of course, the battle was, the victory was from von Neumann group, because today we never use Fermiac to generate random numbers or to make Monte Carlo. We use electronic computers, and this is the correct method to do. But this method of random number generation has some drawbacks. Let's see an example. If I take, these are my initial numbers, or seed, 27. It's a 2-digit number, so A is 2. I square it and I get a number, a 4-digit number. If it's not large enough, I put 0 here. So I have this 4-digit number, and I take the central digits that are form the number 72. So my first random number is 72. I use this to recalculate the next one. So I square it, get this number, select the central digits, get 18. This is the second random number, and so on and so forth. So I get this series of numbers, and these are the random numbers generated in the series. What is the problem? The problem is that after some time I get 0, 0, 2. I square 0, 2, I have a 4. The central digit is 0. So my random number is 0. When I go back to the first step, I have to square 0, and 0 squared is 0. So this is a fixed point in the series. And this is illustrated by this diagram. I have a first random number, I generate the second, and so on, until I have a number that will generate itself in this method. So this is a fixed point. You don't need it to have only fixed points. You may have also cycles. So you have a series of numbers, and then from one of these numbers, you generate one number that was already generated before. So you are constrained to this cycle forever. And this limits the reach of the series that you can get with methods like this. So this is a problem in random number generation, and one of the main features that we have to be aware of in random number generators is the periodicity of the numbers of the series. Okay, if you need Monte Carlos with a large number of sorted, a large random number sorted for your calculations, you need large periodicity, and of course, as we see, this von Neumann method is not good enough. Fortunately, there are modern generators like linear congruential generator, known as LCG, which comes in most of the modern programming languages. So probably when you use the random number generator in your language, it's LCG method. And this method is the following. You have an initial number, and you multiply by a number that you decide, a factor that the method can define, plus some constant c, and divide it by m, and take the rest. Okay, the remainder of the division. And this is your random number. You can even normalize it. You take the rest and divide by m. It will be always a number between 0 and 1. And then you get the number you generate, you put here. You put here again, and recalculate it, and you obtain a series of random numbers in this process. Okay, so it's a recursive method, just like the von Neumann. But the advantage of this one is that the periodicity is much larger. It was proved mathematically. And you can know, more important than knowing that it's large, you can know what's the periodicity once you have A, M, and C. Okay? So this is important to know the periodicity of your random number generators. And this practically solves the drawback of the method that we found by von Neumann. Well, but there is another problem with CG, is that in many times what you want to do with this random number is not to use the random number directly, but build a vector with in a space with dimension d. Okay, so you generate d random numbers, and these are the components of your vector in a space with dimension d. And this is a little bit different because you want that the vectors v are randomly distributed. This is different from the series of random numbers a series of numbers be randomly distributed. And this is related to the dimensionality of the series. What was found not much time ago, and it was found studying this method, this generator called the RANDO, that was developed by IBM using LCG. And this was the problem that they found when they plot the dots, the vectors, or the position of these vectors in a space of dimension d. What they get are series of dots like this, and this is not random. So this is far from. So what we learned in this class is that there are some features of pseudo-random numbers generators that we must care about. And these are uniformity of the distribution. And this is related not only to the fact that it's approximately constant or constant to be really a very good number series, but also with the scale that you need. So the number of digits in your random numbers. Periodicity, that is how many numbers of the series you can get before it starts to repeating the same series. And dimensionality is how large are the space where the vectors built with this distribution can be found. Okay, fortunately, there are a number of tests of random number generators to help us in selecting the most appropriate. And this is the topic of the next week.